Hello, my name is Luke Weston from Wellington High School, and this is my presentation of the Wilberforce pendulum, a complex motion analysis. Here is a video of the phenomenon. As we can see, as the pendulum moves up and down, there is also a change in angle from the bottom of the rig. The Wilberforce pendulum is a type of simple harmonic oscillator where the energy in the system oscillates between translational and rotational kinetic energy. Hooke's law is a law of physics that applies to many types of elastic systems. It states that the force needed to extend a spring by a distance x scales linearly with respect to that distance, where k is the spring constant, how stiff the spring is. This is not only true for extension springs, but also for torsional springs. This is shown here with the equation T equals negative k theta. Hooke's law is a very good demonstration of simple harmonic motion, as force and extension are directly proportional. Simple harmonic motion is a type of periodic motion where the restoring force on an object is directly proportional to the displacement. In the case of this problem, where the system can move from equilibrium in two dimensions, rotation and translation. If the Wilberforce pendulum rotates, the restoring torque increases up to the limit of proportionality and then rotates in the other direction. This is the same for the vertical translation of the pendulum. An extension spring is the spring we are all used to. As the spring is extended, this force exerted in the opposite direction increases linearly, following the relationship F equals negative kx. Here, the equation for the time period of the spring's oscillation is shown here, as well as the frequency. From these I can see that as mass goes up, the time period goes down. A torsional spring is a spring that works by twisting. When it is twisted about its axis by an angle, it produces a torque proportional to the angle of twisting. This is shown by the previously mentioned equation. The frequency for torsional springs is shown here, as well as the time period. The spring that I'm going to use is a helical spring. Most helical springs, when extended, have a torque exerted as they rotate. But why? The reason the spring rotates during its motion is due to the properties of the springs, in that as the spring extends, it also twists the metal very slightly, decreasing the radius of the spring. This means that the spring's equilibrium position for the spring's rotation must change, and therefore a restoring torque is going to be exerted on the spring, which will result in a rotation. A spring collar is a great example of a spring that, when rotated, has an extension. This is similar to the effect that occurs when the Wilberforce pendulum bounces up and down, coiling and uncoiling. It can be seen that, when the spring collar is at equilibrium, the collar does not fit on the barbell, but then when you change the angle of the spring, it will exert torque to restore the spring to its equilibrium position. This changes the radius of the spring, and now, as can be seen from the spring collar now being able to fit on the barbell. For my experiment, I'll be using a slinky. I used a slinky as the way that it extended from the ceiling meant that it had a state of equilibrium that, when weighted, had already undergone some extension already. I wanted this, as this meant that the spring is pliable without adding too much weight that would permanently warp the spring, allowing rotation. I noted that a spring that is too stiff and short will not have the same rotational motion as using a slinky, as the material is not able to twist and rotate as well as a longer, more pliable spring that results in much more rotational motion, and therefore will have more measurable movements due to this. Two motions are described as being coupled when they interact with each other. As the Wilberforce pendulum extends, it also exerts a torque on the spring, making it rotate. This means that the system is coupled because the extension of the spring is linked to the torque that the mass experiences, and therefore the rotational motion. Rotational inertia is the resistance of any physical object to any change in its angular velocity. Its equation is delta I equals delta mr squared. Inertia also affects the frequency, which is the inverse of the time period. For my setup, I need to change both the rotational inertia of the system as well as the mass, I. In order to change the rotational inertia, I attached long arms to it in order to be able to change the radius that the mass is placed at. This is so that I can understand the relationship between the two coupled systems and the efficiency of energy changes between the two, and hopefully find the best inertia to mass ratio. For my setup, I first found a spring that, under its own weight, rotated lots while bouncing. Then I attached two arms to it. I chose to have two arms as opposed to one arm, so that the system does not have one axis with more rotational inertia than the other. Doing this made the angular position of the pendulum much more stable. While testing, three initial variables matter: the extension from equilibrium, the weight of the mass on the arms, and the distance from the center of rotation the masses are. I kept the extension from equilibrium the same over all of my tests, and used a mirror to measure the rotation from the bottom, while still being able to see the change in extension. To measure my rotational inertia, I used a spinning tool to see how the system resists spinning motion. I dropped a weight attached from a string to the system from a measured height and recorded the time it took to reach the bottom. Using kinematic equations, I can find the acceleration, then the angular acceleration using the radius of the circle that the string was drawn around, and then use the tension in the spring to find the rotational inertia of my object. I first measured the system without my rig, and then with, the difference being the rotational inertia of my rig. Whenever I added mass onto the arms, I could then calculate the new rotational inertia added to the system using the equation I equals mr squared. Then I can simply add the extra inertia from this effect to my inertia of zero value and get the total inertia of my rig. To find my spring constant, I used the equation F equals kx, so I knew finding the gradient of a line in an F versus x graph, I will have found the spring constant. In order to do this, I attached masses to my spring and recorded the distances it extended to. Here my measurement bars represent the measurement error. Here my error bars represent the measurement error. I used an accurate scale and a ruler accurate down to a millimeter. For my experiments, I would expect to see a relationship between the rotational kinetic energy and the vertical translation, be able to identify beats as the two harmonic systems interact. For example, my rotational translation and vertical translation would ideally have a relationship, whereas one goes up, the other goes down. For all my tests, I used Tracker to track the videos I took of the pendulum as it oscillated. From these videos, I obtained these scatterplots of the rotational motion and the translational motion. It can be seen here that generally, the maximum of one of the graphs coincides to the minimum of the other. In order to identify beats, I made all the negative displacements positive, obtaining these graphs. From these graphs, it is easy to see the frequency of the beats. This coupling term accounts for the fact that the energy in the y direction is dependent on the energy in the angular direction, and vice versa, whereas the magnitude of this effect is dependent on the properties of the spring. It is defined as the newtons per radian, so in order to find the coupling constant, I loaded my pendulum with weights and found the angle at which it rotated for each weight. The gradient of this line is the coupling constant. I did this again with no extension to find my torsion constant, which came out to 2.1 Nm per radian. For my equations of motion, I firstly had to acknowledge the form of the potential energy of coupling. There is a clear link between the angle theta and the vertical displacement y. The epsilon in this equation represents the coupling constant, which I have measured prior. The way that I get my forces is by differentiating the energies. This can be explained by using units of energy. As work equals force times distance, if you differentiate both sides with respect to d, it yields the equation. The first differential of work equals force. The other parts of my equation are obtained by taking the first derivative of the potential energy of the spring plus the first derivative of my potential energy of coupling. This gives me two second-order differential equations that I can solve to find my equations of motion. To find my equations of motion, I found a university paper that solved the same equations I had, using Laplace transform, a complex mathematical technique that is used to solve differential equations. Here are the equations in Laplace space, and here are the final equations of motions that I used to model my pendulum. Here we can see that when plotted, the model successfully graphs. For example, the test of 0.2 kilograms on the arms at a radius of 0.16 meters. It can be seen that it gives a very good correlation to the theoretical graph. The discrepancies in my data is due to unwanted energy loss through friction and vertical movement that detracts from the y movement, although I strive to keep these constant. The next steps in my investigation was to investigate how different masses and inertias affected my results. My main goal was to find what a mass and inertia resulted in the most efficient energy transfer. For this, I needed more data. For my updated testing setup, as I knew I needed to obtain a lot of data and that tracking each video was slow, I attached my phone to the pendulum. This allowed me to use Firefox, a phone app that allows me to use my phone's accelerometer and gyroscope to track the vertical acceleration and angular velocity of the pendulum. As I'm using my phone's accelerometer, this means I must use a numerical method of integration in order to obtain the velocity and position data. While I was looking at my data, I was trying to find the numerical method that was most numerically stable. After testing all of the different methods and looking at the error as time went on, I was able to choose leapfrog. This integration method calculates the velocity forward half a time step, and then using this to find the position and velocity one time step forward. Then, for my angular velocity data, semi-implicit forward Euler proved to be the most numerically stable, with the least accumulating error, so that is what I used. In order to find the frequency of beats, I simply took how many times per second a peak with maximum amplitude was reached. I did this both for the angular and positional data. By adjusting the mass in a moment of inertia, one can match the frequencies of linear and rotational oscillations. This gives a slow transfer of energy, giving a gradual shift back and forth between linear and rotational motions. The transfer of energy, a properly tuned Wilberforce pendulum, is almost complete, implying that one mode will nearly cease oscillations momentarily, while the other mode is experiencing large oscillations. From this, I know that when the ratio of the frequencies is equal to 1, then the pendulum will undergo the best transfer of energy and the greatest effect. Here are the results I obtained from my testing and data analysis. It can be seen that the data produces a saddle surface, with the lowest points having a ratio of around 1. This shows that at the lowest points on the graph, the pendulum is undergoing the slowest, best energy transfer, giving a gradual shift back and forth between the variables. It can be seen here that in this graph, where the oscillations are clean, always going from a maximum to a minimum and back to a maximum, very smoothly. This is what the Wilberforce pendulum is made to show. On the other hand, let's look at this gross individual here. These graphs show that as there are hardly any minimums, there are no moments where the motion is purely in one direction. There is only a homogeneous motion back and forth, a very bad demonstration of what the Wilberforce pendulum is made to show. Here is another example of a bad display of the Wilberforce pendulum. Again, no obvious minimums that create the periods of motion and indicate slow, complete energy transfer. Here is an example of a badly tuned Wilberforce pendulum. You can see that there are no obvious points where one axis of motion is at a minimum and the other is at a maximum. Here is an example of a well-tuned Wilberforce pendulum. Here there are very well-defined periods of motion, demonstrated by the fact that there are moments where the motion is purely vertical and other moments where the motion is purely rotational. In order to compare my experimental results and my theory, I need to use the Fourier transform in order to extract frequency data from my equations that I derived using the Laplace transform. For this, I used MATLAB's spectral analysis tool, Fast Fourier Transform. This allowed me to put my equations for displacement and angle, and from that find the frequencies. However, in order to analyze this Fourier transform, I need to acknowledge the modes of motion. In the Wilberforce pendulum, there are two modes of oscillation. These motions correspond to two scenarios: the spring extending and rotating with the spring, and the spring extending and rotating against the spring. I refer to these as the symmetric and anti-symmetric modes. The difference between these frequencies of these modes is the beat frequency. Now I have acknowledged the modes of oscillation, I can use the Fourier transform of my equations, linear and angular equations. Here I have labelled the symmetric and anti-symmetric modes. I can now find the frequency of the angular and translational beats by finding the difference between these modes. Then I can take the ratio here and make a graph of my calculated points and compare it to my experimental graph. Here are the two final graphs for my mass versus inertia versus ratio of frequencies graph. Although the experimental graph is a little low resolution, you can see that both of the graphs seem to agree that the best inertia to mass ratio is around 0.032 kilograms and 0.0006 kilogram meters squared added to my rig. For my calculated graph, there is a very small amount of error, mainly in measuring the distance, mainly in the measuring of the mass and distance, as well as in the calculating of the spring and coupling constant. However, adding error bars overcomplicated the graph, so I chose to remove them in order to keep the graph simple. This is the same for the experimental graph, but with a fair bit more error, mostly from measuring the frequencies by hand. In conclusion, through testing the behavior of the Wilberforce pendulum with different masses and rotational inertias, as well as having a mathematical model that matches the data that I have obtained with some discrepancies, I've also done an analysis into finding the best mass to inertia ratio for optimal energy transfer. Because of this, I feel that I've done a well-rounded investigation into this phenomenon and how it depends on relevant parameters. Here's my bibliography, and thanks to these people.